My name is Nicole Terc. I'm an Android GDE and also a tech lead at HubSpot. And you can find these ramblings and much more on my GitHub profile. But with this out of the way, let's take a look at what are we actually going to be doing today. And the answer to that, of course, is we're going to be making some dancing chip. And in order to make them, we're going to need three things. We're going to use animations, we're going to use gestures, and we're going to use sensors. And how are these three things going to mix together? Let's take a look at our chip strategy for the day. In this case, it's going to be pretty straightforward. We're just going to use some information from gestures, that is, tapping around, flinging things, dragging things. We're going to get some information from sensors for whatever you have in your phone. And using this data, we're going to create some fun, and I hope fun for you as well, animations. Now, all of the code that I'm going to show is actually going to be working for Kotlin multi-platform as well, so take a look at that. But with that, let's start in our first block, and let's talk a bit about animations. And the part I want us to focus in is actually, how are we going to make these animations? Whenever I start thinking about creating animations in Android specifically, or Kotlin multi-platform in this case as well, I actually follow a process. And that process involves answering three questions. And those are what, when, and how. What properties do I want to animate? Do I want to change color? Do I want to change sizes? When do I want to make this change happen? When I click a button, when I tap on it, when I do anything on the screen? And how am I going to be changing these properties as well? Like, in this case, I am basically just toggling between two states from big to small. Now, after answering these three questions and translating them to code, I usually add a 4 optional step. And that is, basically, play around and have fun. Move things around and see what happens. But what are we actually going to use to create these animations? The answer, of course, is we're going to be using some animation APIs. So if you haven't already, I highly recommend that you take a look at the Jetpack Compose animation documentation, where you're going to find all the information about them, we have a lot now, and also our trusty flowchart for picking your animation API. I know it looks daunting and it's a bit lengthy, but it works really good. The only thing you need to do is, of course, start from the start, navigate for all the questions until you reach your use case, and when you do, you're going to get right there the API that you need to use. Which in our case, since we're going to be working with gestures, the API we need is animatable, which is a coroutine-based API. Cool. But with this, I think it's enough about talking about theory, about things about animation. I think we're done with that. So let's start seeing some code. So let's dance. Small disclaimer before we move forward, though. This chip is actually a canvas. So all the code you're going to see here, you can replicate using your favorite composable. You can use a box, you can use text, you can use images. But for now, I'll stick to the chip. It's kind of already in the name of this talk. So as I was saying, let's dance. And in order to start dancing, let's move to our first gesture moves. Let's ease into it. So let's go for a classic. Let's do a tap move. Since we already know what we need to do, we need to answer our three questions here. What, when, and how. So in this dance, what we're going to be doing is changing our scale. When, whenever you tap into it. And how, we're basically just toggling between 1 and 1.2. Why these values? Because I like them. There is no specific reason behind them. Cool. Now that we know what we need to do, let's translate this into code. A first implementation of this logic will look like this. Basically, what we're doing is defining our property, which in this case is going to be scale. After doing that, we're just going to pass this property to our composable. Important thing here, I highly recommend that you use lambda-based modifiers, especially with animations, so you prevent recompositions. Once we have our scale defined, our composable, we're just going to trigger this animation, which is basically whenever we click on this chip, we're just going to update the scale. That's it. Pretty straightforward, right? And if you run this code, you're already going to have an scalable chip. Cool, right? But there's a glaring issue with this code, And that is that we're actually not animating anything yet. So let's fix that issue. Since we said we're going to be using animatable, the only thing we need to do is, in that scale, instead of creating it as a straightforward float, we're just going to create it as an animatable. You're going to need to wrap it with a remember, and since now this is an animatable, instead of straightforward set the new value, we're going to need to call a function called animateTo. And of course, since I said it's coroutine based, whenever you call this function, you will need to wrap it in a coroutine. That's it. I just changed it 2 lines, and with those 2 lines, you're already going to have an animation. That's it. That easy. So now you have no excuse to not add animations everywhere. Cool. But this transition is still kind of bland, so let's have some fun with it. And whenever I think about having fun with animations, I usually just beeline to animation spec. Animation spec is an optional parameter in most of these APIs that is basically going to tell how this animation is going to play. I'm not going to go too deep into it. The only thing you need to remember is that all of these animation specs, there are a ton of them already out of the box. You can use, for example, Tween, which is a time-based animation spec, or Spring, which simulates a bouncy spring, or one of my favorites, keyframes, which lets you basically define some keyframes in your animation that your animation needs to hit. Cool. But now that we know that there's some animation specs out of the box, let's see how to use them. The only thing I need to do here is basically just define my animation spec. In this case, I'm just going to create a spring that is going to be really bouncy, but also really stiff. And like that, by just changing an extra parameter, you have a totally different animation. Now, you can play around with these animation specs and basically change things and see what happens. And just by doing that, again, just 1 parameter, you have totally different animations without needing to touch anything else. But for now, I think that's it for the tap to scale. Let's move into our next dance step, reposition. Because someone once told me that staying still in the dance floor is not cool and you need to move around. So let's do the same for the chip. Let's answer again our 3 questions. What are we going to be changing? In this case, it's going to be position. When are we going to be changing it? Whenever we drag on it. And how are we going to be changing it? Well, I'm just basically going to follow the finger around. Cool. So let's translate this again into code. What is happening? Yeah, okay, dance music, sure. Cool. So once we have the idea of what we're doing, we're just going to have something like this. We, again, need to define our property here, which in this case is going to be translation. Can we cue the music? It's distracting. Anyway. Yeah, sure, let's just dance along, whatever. So the property we need to define here is translation, which translation is going to be the change from your original position to the new position. In this case, I'm again defining as an animatable, and as you can see here, instead of creating an animatable straightforward, I'm actually creating an offset with an extra parameter. And that is because animatable doesn't have an out-of-the-box offset constructor. But don't worry. Whenever you find yourself in a position where you're creating an animatable and Android Studio is complaining, the only thing you need to do is move to the generic one and pass a vector converter. I guess we dance. So the vector converter is also out of the box. So whenever you find yourself in this position, just check if there's not already a vector converter available for you. Cool. Once we have this translation set, we again need to set it in our graphic layer. Don't forget this. I tend to forget to define this and just jump into the implementation of things. So remember this. And in order to make our chip draggable, the only thing we need to do is use the draggable 2D modifier. Now this draggable 2D is already going to have all the logic for calculating the dragging animation, the dragging gesture in our chip. The only thing we need to pass is a draggable state. Now this draggable state is going to contain a lambda that is going to react to each dragging update in your composable, which in our case translates to basically updating translation to this new value. Important thing here is that instead of using animate to, I am using snap to. And why am I using snap to? Because I don't want any delay from the gesture with my finger to the movement of the chip. So snap to, what it's going to do is going to forgo all the animation values, forgo animation specs, and just move it straight away where I want it. So it's kind of like a no animation animation. You just move there. And whenever you're working with gestures where you don't want any delay from the input, you're going to want to use snap to. Okay, going back to the full code, this is all the code, and I mean it, just copy-pasted from my repository that you're going to need to make draggable things. Cool. Okay, sure. Anyway, as I was saying, this is the only thing you need in order to make things draggable. It is pretty powerful, and there are other modifiers that you can play around besides the 2D. But in this case, since we're moving in a 2D space, that's why we're using this one. Cool. But for now, I think that's it for drag. In order to play around with these dragging modifiers, let's move to our third step. Fling and back. Now again, let's answer our 3 questions. What are we going to be changing here? Again, we're going to be changing our position. When are we going to be changing it? Whenever I fling on it. Now, a fling gesture, if you don't know what it is basically when you're scrolling a list in your phone, which I hope everyone here has done, and you lift your finger and the list keeps scrolling, that's a fling. Now, how are we going to be animating this fling reaction? We're basically just going to fling the chip, let it move. But whenever we reach one of the borders of the screen, let's move it back to the center. Okay. Okay, cool. So let's translate this into code with some more music, I guess. If we translate these questions into code, it will look like this, which basically is our draggable code as before. The only thing we need to change in order to make this fling is we're going to need to change that draggable to the modifier. And how are we going to change it? We're basically going to pass the optional property onDragStopped. This onDragStop parameter is going to accept a lambda that is basically going to be called every time the user leaves a finger from the screen. It's already going to do all the calculations for the velocity of the finger and everything else, so I don't need to care about that. I just need to react to it. And to do that, we're going to create our fling move, which is our dance step. So how is this fling move going to look like? It will look like this. I know, a wall of text, but let's break it down piece by piece. The first thing we need to do is we need to calculate where our chip would end up if we let the fling go. In order to calculate this new position, we're going to use a really cool API called decay. Now, decay is going to be really helpful whenever you want to calculate future positions or future animations, whenever an animation is going to decay over time, okay? So again, we're going to create this decay, just using remember the decay, and with this, we're just going to calculate our target value. We need to pass our velocity, which we already got from our modifier. We need to pass our initial position, because we need to use it for calculation. And again, I'm passing the vector converter, because offset is not an out-of-the-box thing. Cool. Important thing here is that this target offset is just a calculation. We haven't animated anything yet. But let's do that now. The first thing we need to do is check if this target offset is still in the bounds of my screen. And if so, we're just going to animate that decay. We're going to let the chip just fling, using the animate decay function. If my chip instead is going to end up outside of the borders of my screen, we're going to be doing 2 things. First, we're going to animate to the border of the screen, and after that, we're just going to animate back to the center. And with this example, you can check, well, you can see how flexible this animatable API actually is. Because just creating as a coroutine, calling one after the other, I can compose my own personalized animation without much trouble. In this case, as I said, animate one side. Once that's finished, it just calls the next line. And that's it. Just running this code, which again, looks a bit scary at the beginning, but it actually isn't, you already have fling and back. And that's it for the step as well. you of course can play around with animation specs, changing the velocity, and changing a lot of things, but I'll leave you that for you to discover. And with this, I think we're done with the gesture moves. Let's move to our last block, sensors. Now, whenever you're going to be working with sensors, you will also want to follow a process, which in my case basically involves 3 steps as well. And that is, first, I need to pick a sensor, what I'm going to be working with. And don't worry, there are a lot of them, and they're fairly well documented in both Android and iOS. Once you have picked a sensor, you need to start listening to the sensor data it provides. And once you have that, you're basically going to start consuming the sensor events from it. Now, something important to call out here is that, of course, the sensor events are going to be different from each of the sensors that are going to be there. So if you're playing with the gyroscope, for example, you're going to get some rotation coordinates. But if you're playing around with the temperature one, you're going to receive temperature in degrees. So something important to do whenever you're starting with this is actually understand what type of data you're going to obtain. Cool. But in order to do all of this into code, we'll need a plan. And since, as I said, I am working with Kotlin multi-platform, this translates to creating a multi-platform sensor manager. And since Android and iOS have different ways to consume and create events, because there are different platforms, it seems, we're going to, of course, need to create an Android sensor manager and an iOS sensor manager. But let's translate this again into code. An easy way to create this multi-platform sensor manager is to create an interface, which in my case is just going to be called multi-platform sensor manager because naming is hard, and it's going to contain 2 functions. One, register listener, which is the one you're going to want to call whenever you're going to start listening to these sensor data and events. And the other one is onRegister all. Now, this onRegister all is pretty important, and that is because using sensor is pretty expensive. And even if your app is in the background, the sensor listeners are going to keep sending you data. So don't make your users mad, don't drain their batteries. Remember to stop listening to sensor information if you no longer need it. Cool. Now, since this is an interface, I need a way to, of course, provide the sensor manager to the code. And an easy way to do that is using expect functions. Since I'm using compose, I'm just going to create a composable expect function that is going to give me this sensor manager. In this step, of course, you can just upgrade this, and use your favorite dependency injection framework for this. But for an easy and simple use case like mine, this works. Once you have this expect function, the only thing you need to do is in both Android and iOS, you need to create their own actual functions that are going to pass their actual implementation for both Android and iOS sensor managers. And that's it. But of course, each of these are going to have a different implementation. Let's take a look at those, and let's start with Android. Whenever you're working with sensors in Android, the thing you need to start with is getting a reference of the sensor manager, the real one from Android. It's a system service, so you just call it as a system service. And once you have that, if you want to register a listener to it, you're going to need to do 2 steps. First, you need to get the default sensor of that type. And if that exists, because not all devices have all the sensors, you're just going to register a listener to it. And that's it. You're going to start receiving data with it. Once you have that, of course, in order to register things from it, you're just going to go for each of the sensors, or each of the listeners that you created, you're going to register from them. And that's it. Of course, I'm omitting some of the lines of code here. That's why some of those things don't make a lot of sense. But I invite you to take a look at the full implementation in the code. But the gist is that you get the sensor manager, you get your sensors, register to them, and when you're done, you use onRegister. That's it. So let's take a look at how iOS does things. And something that I found really interesting here is that in comparison to Android, where you only have one point of access for sensors, in iOS, you have different sensor managers depending on the type of sensor you want to consume. So if you want to play something with position, you will need to get the motion manager. If you want to check if your user is running or swimming or walking, you will need the activity manager. If you want to count steps, you need the pedometer manager. And if you want to check for ambient light, you will need the sensor reader. Which, yeah, the name changes because this is actually part of SensorKit. And in order to use this one, you will actually require a paid Apple developer account because you need to play with provisioning profiles and things like that. But I don't delve into that. Take a look at the code because all of this require different permissions. Cool. Once we have the reference for our managers, whenever we register for a listener, since we have different managers, we will need to check which type of sensor we're going to use and in order to that, we're just basically going to register to the correct manager. I know it looks worthy, but a lot of those follow the same structure, basically. So let's take an example with accelerometer. In order to start listening to accelerometer events, the only thing we need to do is get the motion manager, check if there's an accelerometer available, kind of like in Android, you check if the sensor is there, and if so, you just start listening to those events. That's it. Of course, in order to register for all of these events, we will need to go for all our managers and register events from them. You can improve this code checking if you're registered to something or not, but for the sake of just, brute force approach, you can just unregister to everything. It won't crash. Cool. And with this, that's the iOS implementation. It looks a lot lengthier, but it's the same gist. You get your manager, check if it's there. If it's there, you just register. And with this, I think we're done with our multi-platform sensor manager. Let's go back to dancing, and let's create our first sensor move, rotation shift. How are we going to be doing this? Let's answer again our questions. What are we going to be changing? We're going to be changing rotation. When are we going to be changing that? Whenever the device orientation changes. And how are we going to be doing that? We're basically just going to mimic the values from the sensor. And that's it, right? Well, not quite. Because as I mentioned, we have actually a zero step, which is we need to understand what values are we going to receive from our sensors in order to actually play with them. So let's take a look at how this orientation sensor data looks like. And let's start with Android. If you take a look at the documentation, you will arrive to this. Whenever you start listening to these orientation changes, you're going to receive three values. You're going to receive azimuth, which is the z-axis rotation. You're going to get pitch, which is the x-axis rotation. And you're going to get roll, which is the y-axis rotation. Now, let's take a look at the iOS side of things. Again, you're going to get three values. You're going to get yaw, which is, again, the z-axis rotation. You're going to get pitch, which is the x-axis rotation. And you're going to get roll, which is, again, the y-axis rotation. It seems similar, but if we put them side to side, you're going to see that they're not quite the same. They're similar, but no. You're going to see that in one side, we have the minus z-axis, and the other one, we have z-axis. The value ranges are also different. But don't worry. If you get this case, the only thing you need to do is grab one of them, follow that as your source of truth, and just map the other one to that one. And since I, of course, started with Android, I just basically mapped the iOS to that. In order to make this mapping easier, the strategy that you can follow is basically go and create a shared data class, which in my case looked like this. I just created a data class called device orientation, which contained my azimuth, pitch, and roll, and basically just have some helper values there as well to convert this to degrees. Cool. And since I don't want to be doing this mapping every time I register to a listener, you can actually just go to your sensor manager and create an extra helper function called observe orientation changes that is going to contain all the code and all the logic in order to map these things. All the heavy lifting will happen there. Again, I won't go too deep, so if you want to check the real implementation for this, take a look at the code. Nice. But with this, I think we're fine already understanding all our orientation changes and how this works. So let's go back to our rotation shift. An implementation for this will look like this for starters. Again, we're defining our animatables for the properties we're going to change. In this case, rotation in each of the axes. After that, we're assigning again in our graphic layer these values. Again, remember to assign them. And after that, in the how, this is where our sensor manager will come into play. It will just look like this. We're going to get a reference to our sensor manager, and we're just going to observe these orientation changes because all the heavy lifting happening there. And whenever we get an update, we're basically just going to update our properties. Important thing here, as you may have noticed, is I'm calling each of the axes in a separate coroutine. And that is because I want all of these axis animations to happen independently. If I call them all together, I'm going to end up with an animation that is going to be really clunky because it's going to try to animate first X, then Y, then Z, instead of doing them all together. Again, I'm using a snap-to because I want to mimic exactly the rotation. I don't want any delay. And I'm just going to pass the values from the orientation. Important thing here, remember to use degrees because all your sensor data is in radians. Just make sure you change them correctly. And that's it. With these lines of code, we already have a rotation shift. Cool. And small interlude here, if you're wondering what I am actually using for this emulator, it's nothing else but the virtual sensor in Android Studio. It's already present in all the emulators from your IDE, basically, and it contains information that you can use to mock rotation and movement from your phone, but also a lot of extra parameters like the temperature or the pressure or light or whatever you want. So those are pretty handy whenever you're playing with sensors. Important caveat here, this is Android. If you want to do the same for iOS, it doesn't have it. I didn't find anything out of the box. There are some libraries and things that you can implement, but that will require some code change. I don't recommend that. Just get a real device and try it out. Cool. Now that we have that, let's move into our last move, shake it. Let's answer again our questions. What are we going to be doing here? We're going to be changing rotation, translation, and scale. Whenever I shake my device. And how? We're basically just going to do a side-to-side roll and then an end wiggle to add some spice in it. Since we're working with sensors again, we will need our 0 step, which is understand what sensor data we need. And in this case, we're going to use acceleration. So let's take a look at that. If you get again into the documentation, you're going to check that acceleration sensor data for Android is going to look like this. You again get information for each of the axes, but in this case, it's acceleration instead of orientation values. Cool. Let's go into the iOS side of things. If you get in the documentation again, besides the different image, you're going to see that there's basically, again, values for our X, Y, and Z axis. And as you can see here, they're exactly the same. So there's nothing to do here. You can just basically consume them as they come. And with this, we're ready to jump into the code for Shake It. We again start by just defining the properties we want to change, using animatables again. Again, don't forget to set them. I have struggled a couple of things here for thinking my animations don't work, and that's because I forgot to set them here. And after that, we jump into the how. For the how, we're just going to get our sensor manager again and register to the acceleration listener. Each of these events is going to contain our X, Y, and Z acceleration. And the next step basically is to detect the shake it, which in my case, since I was not having a great time at the point, I just basically decided to check online to see if someone smarter than me already had a solution. And turns out there was already something. So I just went ahead and accomplated that Java code into Kotlin and just pasted it here. But let's go over it because it's important to understand whatever you're copying and pasting in your code, right? So let's try to explain this. The first step here is basically we're calculating the value of the vector. Instead of having them separated, we're just calculating the value there. It's just a Pythagorean square root thing. Once we have that, we're just going to get a delta and do some calculations to basically do a log code filter. This is basically just going to remove the noise of your values that you're getting, so you're not going to get acceleration values all the time. Once we have that, we're going to do a magic number check just to check how sensitive you want your shake. If you shake it stronger, this number will need to be higher, but if you want your shake to react from lower shakes, you will just make this number lower. Once we have that, we check if that's the case, and if so, your shake has started. If your device was already shaking and it's not accelerating anymore, that means your shake has ended. And in our case, since we're not doing the same as in rotation where we were mimicking these values, we're using the shake as a gesture. Once the shake has finished, this is where we're going to be doing our shake move. Cool. So how does this shake move looks like? Since we're going to be animating these three things and we want to basically make them at the same time, we're just going to be triggering again each of them in its own coroutine for translation, scale, and rotation. In order to do that side-to-side change of values, whenever you see something like that, you should think on keyframes. Now again, I am triggering them in a separate coroutine. So an easy trick to make sure that all of them start and finish at the same time is to ensure that all of them have the same duration. That is just me being lazy, not wanting to create some transitions and things to align them. So this works, believe me. Just basically ensure they have the same duration, they will start and finish at the same time. Cool. And that's it. Basically just adding keyframes. But for the sake of explaining how this looks like, let's take a look at how the rotation keyframes will look. All of them follow the same structure. In this case, I am just basically defining keyframes, setting the duration, and for each of these lines are going to define the keyframe I want at the specific time. So in this case, for example, whenever the fraction is 0 at the beginning, I want the rotation to be 0. Whenever I'm like 25% of the animation, I want it to be at 180 degrees, so just rotating one side. Once I'm at the middle of the animation, I want it back. Once I'm at the other quarter, I want it the other side, and then back. That is also why the target value of my animation is the same one it had at the beginning. I am just basically animating something and going back. Cool. As I said, the other ones are going to look similar, and with this, you already have a side-to-side animation. But we're missing the little wiggle I promised, right? So don't worry. In order to do that, the only thing you need to do is add even more keyframes, which in this case, you need to make sure that instead of leaving them in their own coroutine, you want them to do it one after the other, because you don't want your chip to be wiggling and moving at the same time. You want it to finish the move and then wiggle. So that's it. With just that little lines of keyframe codes, which can be a little bit repetitive, you already have a shake. If I managed to shake it correctly, there you go. And with this, we're done with Shake It. Of course, again, you can play around with animation specs and change some keyframe values to make it more interesting for you. But for me, this is enough. And with this one, we already have them all. You already can tap it, you can shake it, you can fling it, you can chip it. And of course, you don't need to end up there. You can just create more dance steps, and you have more inspiration like spin it, pick it, dim it, step it. The only thing you need to do is basically grab your favorite gesture or your favorite sensor and stamp a fun animation to it. That's my excuse anyway. But for now, I think that's it. Thank you.